Hi guys, welcome back to Data Every Day. Today we're looking at a dataset of Superstore sales, and basically each record represents a different product being purchased at a Superstore, and then at the end we have a column called sales, which is the revenue generated from a given purchase, and we're going to try to predict this value given the others. So let's hop into our notebook here. I'm just going to import NumPy and pandas for working with the data, and then the train test split function and standard scalar from sklearn for preprocessing. Then we'll be using TensorFlow to construct a neural network to handle the predictions, and we'll evaluate the performance using the R² score metric. So let's get started here. I'm going to load in the data using pandas.readcsv, and we can grab the file path up here to the CSV file, paste that in, and we can take a look. So here's the data. There are 18 columns in total. And you can see we have a good number of categorical columns here. I'd also like to get a little info on the dataset using data.info. And we can see here that there seems like there's some missing values in this column, the postal code column. But aside from that, there are no missing values in the dataset. We also, so here's a count. We have 15 object columns, so we're going to have to do some heavy encoding here. And let's start preprocessing. So I'm going to create a function called preprocessInputs. It's going to take in a data frame. It's going to start by creating a copy of the data frame, and then it's going to return the data frame down here. So currently this just makes a copy. We can call it on our data, store the result in X. So X will be the process version of our data. Currently it's just a copy, but now as we add preprocessing steps into this function, we'll be able to see the result below. So first thing I'd like to do is remove some of these columns that we're not going to use. So I'd like to try to build a model that makes predictions regardless of which customer is buying it. So what I mean is I want to be able to take any purchase of a product and see where it's coming from, and then based on that make a prediction without taking into account which customer is buying it. So we could, you see there is some overlap between customers, but I'm going to try to build a model that doesn't rely on that information. So let's drop unnecessary columns to begin with. And so the unnecessary columns are just going to be like the row ID. In fact, we can get a better sense of this if we create a dictionary here that maps a column name to the length of unique values in the column. So I'm doing x.column.unique, taking the length, and then mapping a column to the column name to that. And that's for every column in x.columns. And so this will show us each column name and how many unique values we have in the column. And you can see we have in our data set there are 9,800 total rows. So if we see something like this, that means that this is every entry in here is unique, and therefore it's not providing any useful information because there's no way to draw similarities between examples with this column. So we're going to drop that in the unnecessary columns, row ID, and let's look through here for any others. Country is also useless because there's only a single value. If you have, it's basically the same thing because there's no way to draw any similarities or differences in this case between examples because they're all the same. So we'll drop country as well. And then I'm also going to drop the name columns. So customer name and product name, because we already have IDs for them, product ID, customer ID. In fact, I'm probably not even going to use the customer ID because I said I wanted to do it independent of customer information. So I'm just going to drop them here. I'll drop product ID, and over here I guess I'll do customer ID. Alright, and we're going to drop these columns from axis 1, which is the column axis. And now we can get the result here. You can see we now have only 14 columns, and all the ones we wanted to drop have been dropped. So now we're left with, I would also like to drop the customer specific features. So drop customer specific feature columns. So What I mean is, for example, the order ID. I don't want to know if a product is coming in an order with other items that a specific customer made. So what I'm going to do is I'm going to drop the order ID. I'm going to drop. Wait, I didn't drop customer name. Customer name, not here. These should both be names. Sorry. Both of these are names. And now, okay, this looks nicer. So I don't need the order ID or the customer ID. And that, I think after that, all of our information will be non-customer specific. So I'm also going to drop columns here, just going to be order ID and customer ID. And also from axis 1. Alright, and so this is the data set we're left with. So this looks pretty manageable. I notice we have some date columns here. And then we have a lot of different categorical columns. In fact, I don't know if there's a single non-categorical column here. There are no numeric columns. However, the date columns will give us numeric values when we extract the year, month, and day out of them. So I'd like to focus on these first. I'm going to create a function up here called encode dates. That's going to take in a data frame and a column we'd like to encode. It's going to start by creating a copy of the data frame, and at the end it's going to return the data frame after we've done something to it. So I'd like to point out that we can take a string of date information and use pandas function toDateTime on the string to get back a datetime object which returns the same information but stored in a way that we can reference the year with .year, the month with .month, and the day with .day. And I'd also like to point out that we can pass in a whole column of the data frame with this. So I'll pass in order date, not .days, it should be X. Yeah, we can't do this quite yet, but you can see that the toDateTime function will convert the whole column into datetime objects. Now we can apply a lambda function that for every x we get x.year, and now we can just get just the years. So I'm going to use this sort of scheme to in our function here. I'm going to set the data frame column, df subcolumn, which is whatever we're passing in here, equal to pandas.toDateTime of df subcolumn. And then I'd like to, after we've converted it to datetime, I'd like to create new columns using the .year, .month, .days. So I'll call it column year, the column plus underscore year, like that. That'll be the name of the new column. And then that's going to be the old column, but with a lambda function applied that takes x.year for every x in the column. Then I'm going to do a similar thing for the month and for the day. So this is just going to be month. And down here, these will be day. Alright, so now we'll have 3 new columns, and after we're done with that, we're going to drop the original column that we got these new columns from. And that should encode the dates for a given data frame and column. So in here, we'll say extract date features, and all we have to do is say df equals encode dates. And we're going to pass in the data frame and the column we'd like to encode, which is going to be order date. And then we'll do it again for ship date, which is the other date column we have in here. Now if we run this, take a look, you can see we now have the actual date information as their own columns, and this is in numeric form. And the original date columns are no longer here. So that leaves these guys left to encode. And so they are all categorical. There's no numeric columns here, so we're going to have to encode each one. And we want to sort of figure out which type of columns, of categorical column this is. So we know, based on looking at this, we don't have any binary columns. So a binary column is a column with only 2 values in it, and you can see every one of these has at least 3. And in addition, the next thing to check for is seeing if there's an order between the values in the column. So looking at here, a lot of these do not seem to have any order between the values. They all seem pretty independent of each other. The only one I can think maybe has an order is the ship mode. So let's look at that. We can get the column itself and then type .unique to see what kind of values are in there. And we have second class, standard class, first class, and same day. So this is a little troublesome because we don't know where standard class comes in. We're not sure if standard class is greater than second class or less than second class. And so when you're not sure about this, if you can't be absolutely sure of the ordering between the values, it's probably best just to treat it like a nominal feature like all the others where there's no ordering between them. And the way we will treat such a column is with the pandas.getDummies function. And here we're going to pass in we'll pass in x sub ship mode, pass in a column, and then it takes each unique value, sends it to its own column, and then we have, for each example, a vector that represents the original value of the example using a one-hot encoding. So here, this 1 means that originally had second class. So you can see we have 1, 1, 1 in the second class, and then 1 and 1 over here in standard class. And that just matches up to here where we have second class, second class, second class, and then standard class, standard class. So with this, I'd also like to point out we can include a prefix. This can be anything, maybe mode, and it will just add mode to the beginning so that we know where each of these columns is originally coming from. So I'll actually call it something more descriptive. What we could do is actually just keep it the same as the column name, which is fine. And then it looks like this, and you can see where the value originally came from. Alright, so let's use this in our function that we're about to make. Over here, I'll call it one-hot encode. And it takes in a data frame and a column. We'll create a copy of the data frame again, just to be safe. And then I'm going to create the dummies. So we're using pandas.getDummies. This time, instead of this, we're just passing any old column. And the prefix, we'll keep it the same as the column name. Alright, so now I'd like to concatenate together the original data frame and the new dummies side by side, so axis 1. And that will just add the new dummies columns onto our data frame. And then when we're done, we can drop the original column from which we created the dummies, because it's no longer needed. And then we'll return the data frame. So here's one-hot encode. Let's now perform that. So one-hot encode nominal, I'll say categorical features. And so let's get all the names here of the categorical columns. I think that's all of these. It's important to note that even though postal code has numeric values, this is an object column. Sorry, not object column, it's a categorical column. Because these values, they don't go in ascending order. These are not meant to be interpreted as one being greater than the other, right? So we want to sort of give them their own columns with the one-hot encoding. And see how that goes. So, I guess we can just grab all of these. These are the names of our one-hot, our categorical columns. And I'm going to say for column in a list of all of them. So I'll just go through this, and I can do this better. We'll do it like this. Oops. Oh no. This is taking longer than I'd like. Okay, there we go. Got them all. Alright, now we have it in a list, and for each column in the list, we're going to call one-hot encode, passing in the data frame, and the column here is going to be whatever column we're iterating through. Now we run this, take a look. We now have 3,000 different columns, which is quite higher than what we had before. But all of our information has been encoded as one-hot columns now on the end of our dataset. And you'll notice that now everything is in numeric form. I'd also like to point out that originally we had some missing values in the postal code column, but because we have now one-hot encoded that, the missing values have been taken care of. Simply for the postal code one-hot values, there will just be all zeros across for the dummy columns if there's a missing value there. So there won't be a single one when we're looking at the postal codes. Alright, so we're about ready to go. Last thing to do is to split and scale the data. So what I mean is, first we want to split off the y from our x. So y is going to be what we're trying to predict. So that's going to be the sales column. And then everything else we're going to put in x. That's going to be just dropping the sales column from df and storing that result in x. And then we will do our train test split. So we're going to get 4 new sets of the data, splitting x into x train and x test, and y into y train and y test, using the train test split function from sklearn. It takes in x and y at train size of our choosing. Let's make it 70%. And by default, shuffle is on, which it'll shuffle the data before it does the split, which is very nice. And then we'll include a random state as well to ensure that the shuffle and therefore the split is always done in the same way. And then we can return these 4 new sets of the data instead of just df. We get that over here and take a look at xtrain. And so xtrain is just 70% of the data, and it doesn't contain the sales column. The sales column is contained in ytrain and ytest, and the test set contains the other 30% of the data. Alright, so the last thing to do is scale the data. So if we look at xtrain.describe, the way this looks, it might take a moment. It has to calculate the statistics for each column. Yeah, maybe I won't. Oh, there we go. Okay. You can see that the means and standard deviations of each column are all over the place, and that can confuse some models, especially neural networks, which we're using today. So I'd like to scale the data so that each all the columns take on a similar range of values. And there's multiple ways to do this. We'll use a standard scaler, so scale x, and a standard scaler will give each column a mean of 0 and a variance of 1. And we can fit the scaler here to the train set. I'm only fitting to the train set because I want to sort of pretend I haven't seen the test set yet. As in practice, you wouldn't have access to the test set at the time of preprocessing. And then xtrain is going to be scalar.transform xtrain, and xtest is going to be scalar.transform xtest. So we're going to transform both xtrain and xtest after fitting it only to the train set. And if we return this now, you'll note that xtrain is now stored as a NumPy array, so we lost the nice data frame look of it. So I'd like to turn it back into a data frame after using pandas.dataframe, and we want to specify that the column names should be the same as x.columns. Alright, and now if we run this, we should have our scaled data set, and if we can calculate describe again, it might just take a moment, we should see that the means and variances, that the means are all 0 and the variances are all 1. So means here are all extremely close to 0, and the standard deviations, which is just the square root of the variance, is all extremely close to 1. Alright, so it's looking pretty good. I'd like to now start the training. So I'm going to create a 2 hidden layer neural network, and we'll play around with the number of neurons in each layer, but we can do that by first creating an input layer. I'll call it inputs with tf.keras.input. The shape here, which is the size of a feature vector going into the input, is going to be basically, it takes in one of these at a time, one row at a time. So it wants to know how many values is it taking in at a time. So if we look at xtrain.shape, you can see there's 6,860 rows, and each time it's going to take in 3,102 values. Those are the columns. And we can get that number with xtrain.shape sub 1, so that will give us the number of inputs. And so in here, I'm going to pass that in as a vector. And then I'm going to create our two layers, or two dense layers. So that will be with tf.keras.layers.dense. And we'll give it 128 activations to start, and we'll mess around with that value. And we'll do a ReLU activation. Here we'll pass in the inputs, and then on the second one here, we're passing in X, but it's the same type of layer. Then for our outputs, that will be also a dense layer, but we're only passing one value, which is going to be the predicted price. And because this value can take on any range, as any float, we're going to give it a linear activation, which is just another way of saying no activation function. And then we'll create our model using tf.keras.model, pass in the inputs and the outputs, and then we can print a summary of the model, model.summary. And you can see we come in with a feature vector of length 3102. The weights bring it down to 128, then again to another layer of 128, and then finally down to our final output with one value. And now we will compile the model. So the optimizer we'll use is the Atom optimizer, and for loss we'll use mean squared error, since it is a regression task. And then we will fit the model and store it in history, store the results in history. Xtrain, we're training on Xtrain, Ytrain, and we're going to give it a validation split. So we're going to use 20% of the data for validation. And then batch size will be 32, number of epochs. This I'm going to make it a large number because we're going to use a callback function that will help us out. tf.keras.callbacks.early stopping. And this function will essentially, it'll look at a value. The one we'll give it with monitor here is val loss. So we'll look at the validation loss. Well, so it'll look at how the model's doing on the validation set. And when it notices that the model is not improving its validation loss score after a given number of epochs, so let's say 5, then it will stop the training and restore the weights from the best epoch. So I have restore best weights equals true. I'm also going to include another callback function, which can just help the model converge a little more easily, which will be reduce learning rate on plateau. And so when it's sort of similar to early stopping, except when it notices that validation loss is not improving, it will reduce the learning rate. Alright, so let's do this now. We're going to train this, and our loss should hopefully go down. Alright, so it finished. We have a pretty high loss here. And let's see how this is going. So we're going to get the results. I want to store the main result, which is the loss, in result, or I'll call it loss, maybe. Test loss, I'll call it. Model.evaluate will give us that. We pass in the x test and y test to see how it does on the test set. I'm going to include verbose equals 0, so it doesn't show this loading bar thing. And then we'll print out the result, test loss. I'm going to display it to 5 decimal places and format that with test loss. And it's quite high. It seems a bit lower than what we're getting here, which is good. I don't know. The validation loss should be sort of similar, and you can see around here, which it looks like after the early stopping, it restored the weights from this epoch 3. You can see that was doing the best, or actually maybe this one, but that's sort of similar to what we're getting here. We can also sort of get an idea of how our model's doing with the R² score. So I imported R² score from sklearn. That's going to take in the true answers to the test set and our predicted answers. So I need to create the predicted answers, and we can get that with model.predict, pass in xtest, and I just want to send this down to 1 dimension, so I'm going to squeeze the extra dimension out of it with numpy.squeeze. And this will be a list or a numpy array of all of the correct answers. Alright, and then we will get the R² score, so I'll call it test R2 this way. and then we'll print out the result. So I'll just type in test r squared score, and I'm also going to display this one to 5 decimal places and format it with test r2. Alright, and you can see, yeah, okay, it's not terrible. It's not good, it's not great. Obviously, it's sort of hard because r squared score is a measure of how dispersed the data is from the fit. And you want it to go up to as close to 1.0 as possible, but you can get much worse scores than this. Sometimes r squared can go into really, really negative numbers. So, our model's doing not great, but not too bad either. And I want to see if maybe changing around with the number of neurons here will help. So we can try bumping this up to 256 to see if having more complexity in the model will improve the results. So it'll just train again. And it doesn't seem to be really doing too much. Let's see here. Oh, it actually went up a little bit. So we could try one more time, maybe bumping this up, and let's bump it up a bit to 1024. Give it a lot of flexibility. It will take a little longer to train that way, but hopefully we'll see some improvement. And that's already looking a little better. This may be the best performance though, so maybe not. Oh, let's see. No, it's going back up. Yeah, it doesn't look like it. Looks like, oh, this was actually, yeah, this was our best. So it's probably going to stop here for the early stopping, restore the weights, and then, yeah, we get basically the same results. So it doesn't look like we're getting much better results, but that's okay. So that will sum up today's video. Thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.